Hello everyone. So today we are going to talk about computer vision in post-disaster reconnaissance. So the first part is about motivation. In real-world disasters, quickly assessing damage from satellite images is critical for effective response and resource allocation. However, we face major challenges. Severe class imbalance across disaster type, high image variability, and overfitting in traditional models. So our goal is to build robust models that can accurately classify multi-level damage, even when the data is noisy and imbalanced.
So we started with EDA to understand dataset. It includes satellite images from hurricane, fire, and flooding, labeled from level 0 to level 3 damage. First, we found a strong class imbalance. Over 90% of flooding and fire images are level 0, while hurricane has more level 2 cases. Also, image sizes vary a lot. Fire images are much larger and move more varied than others. For color and texture features, flooding images are darker, while fire images have strong red tones. In texture, the fire images show sharper edges and more structural breakdown, while the flooding images have more varied local textures. Age density increases with the damage severity, and this confirms that the age-based features are useful for damage prediction. In summary, these findings helped us engineer the features and plan for model adjustments like class weighting and size standardization.
The third part is about methodology and results. So for the task A, we first uniformly process the image into a 64 multiple 64 grayscale image. Feature engineering extracted a variety of information. The color information was extracted through the HSV histogram to help distinguish different disaster environments. The texture features use multi-scale LBP and Gabor filtering to enhance the recognition of local damage. Age features and HOG supplements the overall structural information. So the total of 66 dimensions was used. The model chose XG Boost because it has strong robustness against multiple and heterogeneous features. By adjusting the class weights and decision thresholds, the sensitivity of fire detection has been particularly enhanced. Finally, an 80 to 20 division and a 50% discount stratified cross validation were adopted to ensure the stability and the reliability of the evaluation results. And on the test set, the model achieved a accuracy rate of 99%, and the F1 scores of floods and fires were 0.98 and 0.99 respectively. In the five-fold cross validation, the overall accuracy rate was 97%, among which the fire detection recall rate was slightly higher, reaching 0.99. This indicates that through feature design and weight tuning, we have effectively enhanced the detection ability of fire damage. Meanwhile, the model performs consistently under different data divisions and has a good generalization ability.
For task B, we tried the ridge classifier and finally used the random forest classifier because it handles overfitting well and works with diverse feature types. We resized the images, split the dataset, and used stratified sampling to preserve class balance. And we engineered 70 features and tuned the model using stratified five-fold cross-validation and the randomized search CV function. Our validation model reached a macro F1 score of 0.59, and after retraining using the combination of training and the validation set, we achieved 62% accuracy on the test set and the same macro F1 score, showing good generalization. And we tuned hyperparameters using randomized search CV and focus on the macro F1 score to handle class imbalance.
To furthermore explore the impact of the deep learning model in our task, we start by using a pre-trained ResNet model. To adapt this model to our task, we replace the final fully connected layer with a dropout layer with a dropout rate of 0.6 in order to avoid overfitting, and followed by a linear classifier that outputs the four different damage levels. For the training, we use a dam optimizer along with a weight cross entropy loss function to address the issue of class imbalance. We also integrated a learning rate scheduler and a early stopping mechanism with a patience of 10 epochs to improve training stability and prevent overfitting. Regarding the training setup, the model was trained on a GPU using an 80-20 split between training and validation dataset. The training process was automatically stopped at epoch 9 once F1 score reached our predefined objective. This setup allowed us to achieve stable convergence while efficiently adapting the ResNet model to our specific classification tasks. And the final F1 score we achieved on the validation set was 0.5324. And as shown in the left plot, F1 score fluctuated during the training, but gradually improved, ultimately surpassing our target in the ninth epoch. On the right image, we can see the training and validation accuracy over epochs. The training accuracy shows a steady upward trend, reach about 70%, while the validation accuracy fluctuates more, indicating some challenges in generalization. However, the overall pattern shows that the model was able to learn meaningful features for damage classification. And the last part is the discussion part. From the result of our three models we introduced before, we find that for simpler tasks like binary classification, traditional machine learning models, especially the XGBoost, performed extremely well, achieving around 99% accuracy in task A. And also in multi-class damage prediction, random forest also performs very well, which achieved about 64% of the validation accuracy. While our fine-tuned ResNet model only achieved around 59% accuracy in text B. This result suggests that for this dataset, traditional method may actually generalize better. So in the futures, this automated damage assessment method have great social value and benefit, since it can significantly speed up disaster response, providing more consistent evaluation for the engineers and reduce human exposure to dangerous environments. In the future work, we also aim to improve model performance through data augmentation, explore better deep learning architectures, and move towards damage localization for better and more detailed results. And that is all about our presentation, and thank you for your listening.